So the first presentation is by Mr. Paul Hiew, who is at the left of me. He's the Senior Systems Manager at NSCC. Mr. Hiew joined A-STAR in 2001 at IHPC, managing the Institute's HPC's compute facilities. So when A-STAR Computation Resource Center, ACRC, was established in 2007, Mr. Hiew was reassigned to the center as Systems Manager. So Mr. Hiew was in the working task force when installing the NSCC 1 PFLOP systems in 2015, which is Aspire 1. And in the subsequent year, he transferred to NSCC to continue his career with managing the NSCC HPC compute facilities. So as the solution architect for Aspire 2A project, so Mr. Hiew will be introducing the overall system architecture design of the Aspire 2A system, including the hardware and technology used for the supercomputer. Mr. Hiew, please.
Okay. Good morning, everybody. Thanks for coming down. I'm Paul, as you know. Don't call me Mr. Hiew, it's a bit weird. Just call me Paul. Okay. Yeah. Already have an introduction of myself. Okay. Yeah. Then we proceed to the thing. We have the first system in 2016 for the NSCC. That is a 1 petaflop system. I think I don't need to introduce much because today the focus will be on the second stage that is right in the middle. That is the system that is called the Aspire 2A. Of course, we will be moving on. So once this one deployed, then we will be moving on with the next system just to lay a foundation for futures. Okay. So just pay attention of this one. Basically, we are, because of the constraint of the data center, we actually split it into three. You see, we already have the high-speed interconnect that is linked across the country through the single RAN. Okay, for those who are not familiar with single RAN, I think Professor Francis Lee will introduce that sections. Okay, just pay attention. Right now, currently, the Aspire 1 is located at Fusionopolis, which is right in the bottom here. Now, the Aspire 2A will be located at NUS. Currently, we have a kind of backup over in NTU. So, data is protected in such a way with different locations. Okay, that one I will talk in detail. So basically, these three locations are linked with the high-speed network. This is the Aspire 2A. System is not ready for viewing, but today you guys is the first one to see it. Okay, this is the layout of it. Okay, nicely decorated by Singapore. Okay, so remember these are photos. So for the system itself, it's a 5 times more compact to the Aspire 1. And it's 3.5 times more cores, and then 2 times of the GPU sizing, and there's 8 times of the compute power. So for those who are doing the computational works, yeah, it's good news for you. Okay, so hopefully you can make good use of the system. So pretty much this is the hardware perspective. I will go into this summary with the wordings portion, so that for you guys to easier to digest. I know graphical sometimes times 5 times it doesn't mean anything. So this is the hardcore numbers for you guys. Okay. To pay attention about this this storage, this is something new in the sense it's like the way we use the storage. Okay, I will talk more about that. Let's just pay attention about the 10 petabyte of spinning and then 15 petabyte of nearline. So the data center itself, which will be covered by Vincent later on the second presentations in detail about the data center, but just roughly give you an idea. It is located at I4 at NUS. Okay, the area of the data center basically divided into two. Why? Will be explained in later presentations. Not the whole data center is belong to us. We are co-share with others. Our system is basically the first one will be on over this area. Basically, it's the admin system as well the storage. and then the main compute is on the area A. Okay. For that, why the area A and the area B for the differences, Vincent will cover that. So just to let you know the differences, okay, what are the cover in the area A and area B? So area A, we have the main compute, the 768 nodes. And then for GPU, we have three types of GPU. One type of the GPU is located at area A. Okay, the other side will be on the area B. Why there is the differences? At the area A, the GPU have no local disk, whereas the area B, they have local disk. So for the AI workload, who need to take advantage of the local disk, so the area B will be the one more suitable. And we have a large memory nodes. We have two types of memory. It is how many? 2 tera and 4 tera types of memories. Okay. And we have a special high frequency nodes. This one later Teguh will be presenting about that part. Okay, this is a special kind of things that is about the Kubernetes. So we will be trying to introduce new types of things onto the compute resources. But it's pretty small. We started with small so that we need to understand the workload, because we don't have a profile of this kind of workload of the current system. Okay, this is another summary. Pay attention on the red things. At Aspire 1, we have only 24 cores per node. Right now, you have 128 cores. So for those people who can take advantage of it, yep, good news for you guys. One node, you have 128. For those having problem with scaling your MPI, yeah, this is good news for you. Okay, and then memory will be double compared to the triple. Because currently at the Aspire 1 is around 128, but its usable is 96. But this one is around 512 because of the local usage of the OS. So it will be around 500 kind of memory per nodes. Okay, just to give you a highlight. So of course, yeah, 2 tera is also 128 cores. And then where else the GPU type, we will be having a single socket instead. So because of the core ratio to the GPU will be maintained as smaller, so it's more cost effective in that sense. Okay. So this is the Cray AX itself. I have to do a crude one for the drawing because this is a special in the Cray AX itself, because I think we are the one of the site that is having 2 CDU at the same time, because our hot environments. Okay, Singapore is nearing to the equators, so it's very hot. So that's why we need a 2 CDU to run the system. So pretty much this whole system here is actually almost 5 times of the current Aspire 1. But it only consists of a 4 cabinet itself. 1, 2, 3, 4. Okay, actually the 4th one is only GPU. So in real, it's only 3 to can cover the 20 racks size of the current, but it's 5 times more. So this is how compact is the current technology. So looking at the system itself, lot of pipings. This is because it's a liquid cool. Okay, so those are red one definitely is the hot water. The blue one will be the cold water that are flowing. Do remember the cold water we are talking about is 40 degrees. At least, not 20 or 10, okay? So Vincent will cover that one in detail. So looking at the other side of the thing, so these are the interconnect itself, okay? Somebody is working, so you can have a relative how tall the racks are, okay? Yeah. So this is the CPU nodes. You can see that how packed is it. Each of the system are packed with 4 nodes. So this is how we can manage to get the density out of it. Okay. Usually what you know is per node, per chassis is per node, but this is 4. So this is how the things make it more compact. And then because of the space that we're saving, so we have to use the liquid cool to cool the system. Okay. This is a Slingshot switch. This is a special switch. I think you all knowing about the high-speed interconnect. So this is the HP newly inventions about called the Slingshot switch. So this is there are two types. One is liquid cool. One is air cool environment. So straightforward. Even though you don't need to see my description, you should know which one is liquid cool and which is air cool. So always remember that liquid cool is more dense. Air cool is always fatter. Okay, now looking at the thing, this is the very important. So you can see that there's area A and area B. So the visualization, the storage is all over here, and then the compute nodes, and then the scheduler. So if we're having these two both sides linking with around 2.4 terabytes of transfer speed between this side to the other side. So this is the highly interconnect using the Slingshot itself. Okay. So you can see all the numbers here. I mean, I don't want to bother you to read through all the numbers. You can read through from the slides eventually. So for those who are interested in the numbers, you can go ahead with that. So all this information is here. Okay. So you have to understand, just now you're looking at this 4. It's actually each of them is a cabinet. But in the term of thing, it's called one group. Each of the group have 16 switches. These are the bigger switches. Each of the switches are linked with 16 nodes. Okay? So, although there is a high-speed network, I think this morning Mr. Raj already covered that one. So, you can see that the latency is pretty low over this. So, it's highly meshed. So, you can high-speed interconnect to each other. So, but I think Xingyi will be presenting about the software set. They will benchmark, so you can read more detail how this interconnect behave. So this is telling you each of this switch is actually linked with 16 nodes. Okay, just to give you an idea that how you look at the things. So where's the software stack? Right now we can see that we have already getting most of the applications onto the system. Of course, still pending for some other things. So these are the things that are already on top. So we have already categorized in a different way. We have a system. Of course, this one is more for this for you to like OS, all those things, compiler. But whereas the development, programming, of course, the libraries itself. Okay, plus this libraries. Okay, sorry. Okay, and then you have the profiler here. I think this profiler will be more than compared to the previous one. So, of course, we will introduce in your detail how each of the application works, you know, in the subsequent course, this kind of workshop. Okay, do pay attention that we will be calling for workshops, so hopefully you can all join and then learn more about it. Okay, there are bio tools, there are workflow tools, you know, you have AI, you have simulations applications. So here, I think most of you will be interested. Okay, of course, not all of them in, because some of them require licenses, which we need you when you come on board. You have to sign your licenses agreement with the vendors before we put it on the system. Okay, and then of course other tools of it. Okay, right now, remember just now I talked about the storage itself. Okay, talking about the 10 and the 15, the 10 spinning and then the 15 about the nearline. So this is the things that we're using is called the data management framework. So what we do is that we are having this kind of workload. So hopefully with that, you can move your data, the system will automatically move your data from the spinning disk onto the nearline, for example, to the tab, which is, I know most of you like to just have your data on board, but you actually, most of the time, you forgot it. You just leave it there, okay? Because you say, oh, I want to hold it for future analysis. But usually, once you say you want to hold, usually you will take months. But if this months of things, if I don't have an alternative, I leave your data on the spinning disk, that means it will be costing me a lot. And then you will let other of your colleagues will be suffering to get the performance out of the storage. So that's why we will be using this one to move the data up and down from the spinning disk to the less speed, higher speed storage in order to free up the high speed storage for you guys to use.
The high speed storage will benchmark at supposedly at 190 something.
For the write, 100
bytes per second.
Yep.
So that would be very costly if we keep maintaining a terabytes of storage. So this is
Yeah.
EMS is pushing up to 0.1.
Yes. So I think we all suffer now for the Aspire one. 90% full. You actually, I'm not sure whether you do notice when you're reaching a certain percentage, your storage actually slow down. Okay. I think most of you might not be observing, but we do observe. Yeah, we don't like this thing happen. We've been actively looking for a solution for that. Yeah. Okay. So, yeah. Okay, so it's actually by policy to move. It's not instantaneously. So this thing, you will feel it and then you will know it. Okay? So this is some of the numbers that they are talking about. Okay? So this is how it's going to move from the high speed all the way to the end of the storage. Okay, so it will just keep on moving. So this is currently is what is happening here. So the NSCC Fusional Police 1 is Aspire 1, whereas this is at the NTU. So the data is already, through this DMF, we make a copy of it. Okay, it's not archiving, it's called versioning. So your data will be still readable by you, but it's not on the main storage, that's it. Okay? So, but because of the Aspire 1, the file system, the version are too old, so we cannot kick in the full features. But moving forward, with the Aspire 2A up, this whole infrastructure will be revamped, and all the things will be fully activated. Okay, so you will see more benefit of it. So this is how the data are going to move. Okay, you can study in detail for that. Okay, this is another similar Aspire 1. Actually, you need to move to the I4 before moving to NTU. But all this is already with the high-speed interconnect already connected. Okay. So this is for you. Why? Because, for example, you can see that 2 to 5 years of data, there's quite a substantial 20% is occupying. Whereas if you look at the genome-based users, will be almost 50% is putting there for up to 2 to 5 years, never touch or access or modify. So it's pretty wasting my, sacrificing my spinning disk. Okay, this is the call of early access. So I think Prof. Tan already mentioned just now, earlier on. So this is slides for you, okay, getting ready, yeah. Okay. There will be an online application form for you, okay. So we will dispatch this information, later, directly to you. Okay, this is some of the photos that is on the delivery. First batch, how the whole data center is eventually putting together. Okay, so this is the main storage itself. Okay, so all the hard work that we've been doing. Okay, all the manual works, and so far it's good. Zero casualty. So this is what we always uphold. Safety is the utmost important thing. Okay. Coolers, installing of the Cray EX itself. Okay, this is the photos of it. Okay, this is the final printout. Okay, thank you.